Hello, we're going to go through some examples where we solve a quadratic equation using one of four separate methods. We're actually going to cover the first three. The first one is direct factorization. The second one is called use of the square root principle. The third is called completing the square. There's a fourth one by the quadratic formula, but I will cover that as a separate item. Let's talk about the first one, direct factorization, since it's the easiest. In direct factorization, essentially we're saying that whenever we have two numbers that are being multiplied, our job is to try and find a factor of a times b equals 0 means that if a is equal to 0 or b is equal to 0, then the entire equation a times b is equal to 0. So our job would be to try to find some factorizations. So here's an example. Let's say I'm given x squared minus 7x minus 8 equals 0. If I were interested in solving this by factor, my first job would be to factor x squared minus 7x minus 8 as a trinomial. Certainly you know that since it starts with x squared, we're going to factor it into two binomials that contain x, and then factors that contain of negative 8 that add up to negative 7. Well, in this case, that is x minus 8 times x plus 1. Well, this is the situation where a times b is equal to 0, because if a times b is equal to 0, then either a is equal to 0 or b equal to 0. In our case, that means that by the factorization principle, either x minus 8 is equal to 0 or x plus 1 is equal to 0. Solving each one of these linear factors individually gives us x equals 8 and x equals negative 1. So our solution set is going to be the set x equals negative 1 or positive 8. The next method we want to talk about is the square root principle, which looks kind of like this. Anytime we have an equation in which we have a variable term a squared equal to some number on the other side of our equality sign there, b, then a is equal to the positive or negative root of b, provided that d is a positive number. I meant d, not b. So in this case, let's run through an example where we solve this using the square root principle. In the square root principle, our first job would be to take whatever squared term we have, put that on one side, and any non-squared terms, and move that to the other side of the equation. Doing that in this case is going to give us 3x minus 1 quantity squared is equal to 121. You'll notice that this is of the form a squared equals some fixed number d. So our next job would be to take the positive or negative square root of the number on the other side. Well, the square root of 121 is 11. So 3x minus 1 is equal to positive or negative 11. Now the plus or minus symbol is really a convenience. It actually means that our entire expression is equal to either negative 11 or it equals positive 11. Both of them are legitimate solutions to us because we could take a positive or negative root and square that and get a positive 121 as the result. So this gives us two linear equations for the variable. Either 3x minus 1 equals 11 or 3x minus 1 equals negative 11. If you solve the first one by adding 1 and dividing by 3, or solve the second one by adding 1 and dividing by 3, you get two solutions: positive 4 or negative 10/3. A little bit easier to handle this way. It is a good trick if we can do it, but very useful. The next method we want to talk about is called completing the square. Now, completing the square, we're not always given, so fortunate as to be given, quadratic equations that are in the square root principle form. But it's really useful if we can rewrite it that way. So let's talk about this. The first thing we have to recognize is what is meant by a perfect square trinomial. Well, a perfect square trinomial is one that looks kind of like this. Any trinomial that can factor into x minus or x plus some number quantity squared. X minus 3 squared, notice, is the same thing as saying x minus 3 times x minus 3, and the product of that, special product, is the square of the first term minus 2 times the product of the first and second term, so that's 2 times 3x, plus negative 3 times negative 3, that's 9. So you see, other perfect squares, x squared plus 4x plus 4, factors is x plus 2 squared, x squared minus 12x plus 36 equals x minus 6 squared. So you might be asking yourself, how could I possibly recognize this situation? Well, it turns out that it's very, very easy. In each case, the leading coefficient is always equal to 1, and the term at the end is the square of 1/2 of the coefficient of the middle term. So let's take on, for example, x squared plus 4x plus 4. If you take half of 4, you get 2, and you'll note that the square of 2 is equal to 4, which is our very end term. And the same thing is true for our last one, where we have x squared minus 12x plus 36. We note that half of 12 is 6, and when you square 6, you get 36. Just our very last term. So our job right here is that we can recognize this very easily if we recognize that we have a leading coefficient of 1 and can take the middle term, the term with the coefficient next to x, take half of that coefficient and square it to get the end term. So let's talk about an example where we're going to solve something by completing the square. How does that work? Well, our job is to set up something on the left-hand side of the equal sign that looks like a perfect square trinomial. So our first step would be to move the constant that doesn't give us that perfect square to the other side of the equal sign. In this case, that's subtracting 2 from both sides. In the next term, what we're going to do is we're going to take half of our middle term, so 1/2 of 4 is 2, and when we square that, we get 2 squared is 4. So we add 4 to both sides, giving us x squared minus 4x plus 4 equals negative 2 plus 4. On the left-hand side now, we've got a nice perfect square. This turns into x minus 2 squared, and on the right-hand side, we get positive 2. Now we're in the position to use our square root principle, so x minus 2 is equal to plus or minus the square root of 2. And by isolating x, we're going to x equals 2 plus or minus the square root of 2, which is to say our two solutions look like 2 minus the square root of 2 as one solution, or 2 plus the square root of 2 as our second solution. My last example is one in which we don't have 1 as a leading coefficient, and we ask ourselves, what do we do then? Well, our next job is to get rid of that 1 as the leading coefficient. So here's the way this is going to turn out. We've got 3x squared plus 18x equals positive 10. What we do is we move that constant over just like we did in the last term. But then the next step is special. What we have to do is we have to get a leading term of x squared, and that means that we have to divide every single term by 3 to make that happen. So we're going to get 18 divided by 3 times x in the middle, and 10 divided by 3 on the right. And simplifying that out, of course, gives us x squared plus 6x equals 10/3. Now we have to complete the square. We complete the square by taking 1/2 of 6, which is 3, and squaring that number, which is 9. So we add that as our last term. We're going to get x squared plus 6x plus 9 is equal to 10/3 plus 9. And so we factor on the left. We've got x plus 3 quantity squared. Now on the right, we have 10/3 plus 9. 9 is the same thing as 27/3, so we actually have 37 over 3. And so x plus 3 would equal plus or minus the square root of that fraction, 37/3, x is equal to -3 plus or minus the square root of 37/3. If you remember how to rationalize the denominator right here, that means we multiply the numerator and denominator by the square root of 3 to get rid of that radical in the denominator. So the form of our answer we might like is -3 plus or minus the square root of 37 times 3, which is 90 plus 21, 111, all divided by 3. Good luck.